Thank you, Margena. I want, first of all, to thank Samriddhi and the International Center for Theoretical Science for the hospitality and for allowing the organization of this meeting of such a diverse background. I don't think, maybe like that. So in this talk, I will present probably the first experiment where we are able to observe clustering, the onset of clustering dynamics in an optical system, and precisely in an exciton-polariton quantum fluid. So these experiments have been performed in Lecce at the Institute of Nanotechnology of the CNR, with the main contribution from Daniele Sanvitto and Riccardo Panico on the experimental side, and the theoretical support of Alessandra Lanotte, following an initial proposal by Michal Matuszewski and Paolo Comaron. So let me first focus on the motivation, so why we want to look at these dynamics in an optical system. So first of all, the dynamics of quantum vortices is still an open problem, a very interesting one. We have seen during this conference different models, Luca, Ashton Bradley, previous talk of Michel Wouters. Historically, everything started with superfluid helium, which is the system where we have fully developed turbulence, several long range of scales. Is still also very important for application, cryogenic cooling, for quantum application, for high precision measurements in space, like gravity probe B and spectroscopic satellite. However, the small vortex core makes it difficult to observe the dynamics of vortices. We have this morning another interesting talk by Mathieu Gibert about that. And also it's really challenging to observe turbulence in 2 dimensions in this system. Atomic back, BEC, of course, are starting from the 90s, introduce a new system where you can really observe single vortices, where you have a clean system, really precise estimation of the system parameters. And so it can complement this kind of information. At the same time, in this system is very difficult. So the information about phase is limited. And this prevents a full understanding of the velocity field, for example. So in this sense, optical system can provide new information. The main advantage is the direct measurements of the phase, but also possibility to have a large number of vortices and access to a large statistics. So, for example, we can provide thousands or tens of thousands images to Tapio Simula and this artificial intelligence stuff to measure it. We have also some complexity that is brought by sound waves, and we have, as for atoms, a limited range of scale to observe. But altogether, this system can provide a unified and provide more information about this kind of dynamics. So this is resumed here in this table. Let me just pointing the difference, very different healing length, so the vortex size. And for what is important in the next slide, also the fact that exciton-polaritons are dissipative system. We will see what are the consequences of that. So the outline of the talk is introduction about exciton-polariton, the observation of the clustering process, both through vortex classification and the direct measurements of the kinetic energy spectrum. Then some further analysis about geometrical aspect of these dynamics, and finally conclusion and outlook. exciton-polariton are also known as hybrid exciton-photon states, so superposition of exciton and photon wave function. This is achieved through the strong coupling of a photon and an exciton. This is typically done in semiconductor microcavities, so the photon acquire a mass. This is the in-plane momentum, and the strong coupling with the Bayer exciton produce new eigenstate in the system that are called upper and lower polariton, are separated by the coupling strands between photon and exciton. In this talk, we are mainly interested in the dynamics around this point of the dispersion. So this is the typical structure of the sample. We arrive with the light on the top here. These are two mirrors that are used to confine the electromagnetic field and maximize the enhancement close to the quantum well where the exciton resides, so to achieve the strong coupling. So the dynamics is in this plane is an exact two-dimensional system, and this in-plane momentum, of course, is the angle of incidence and emission of light with respect to the normal to the sample surface. So in these systems, quantized vortices appear like this with a vortex core of a few micron. The direct measurement of the phase allowed to recognize vortices and their sign or rotation. And this is the profile of the velocity field. This is in a rotational vortex with velocity decaying as 1 over r in space. So in the past years, we developed the technique to inject and detect few vortices in the system, both in density and phase, and in time. So these allow us to, for example, to observe the formation of vortices when the fluid hits a defect. You can see both the modulation in the density and the formation of dislocation in the phase. So in this case, the full dynamics is on about 2 picoseconds and on micrometer scale, so it's really small and fast. And actually, this is one of the main reasons why it has been always considered difficult to observe any self-organization of a large number of vortices in this system. So exactly because the dissipation of polariton, photons are leaking out from the cavity, reduce the lifetime of this system. However, recent advancement in the production of high-quality sample have extended the lifetime of this sample. So this proposal from Maciejewski and Komaron through a stochastic Gross-Pitaevsky equation, they analyzed what are the differences between the conservative and dissipative case in the case of injecting a large number of vortices in this kind of system. As a proxy to analyze what are the dynamics of this vortex gas, we have considered correlation, standard measurements, where correlation going toward 1 means that we are approaching on-Sagar condensation, clusterization of vortices, while correlation that goes towards -1 is a sea of dipoles, of vortex and antivortex. So in this case, this simulation showed that with respect to the conservative case, or very long lifetime, when the lifetime is reduced, the correlation still shows an initial increase towards clustering, but then when dissipation prevails, is doomed to decrease towards -1. So in this case, there is also the analysis with respect to the intervortex distance and the, let's say, the density, so the inverse healing, the healing length in the system. You see that there is a maximum. So this is qualitatively explained in this sense, of course, if vortices are too far away, we don't have time to trigger the clustering dynamics, but also if vortices are too close to each other, they will annihilate too fast and will not produce this kind of attraction between same sign vortices. And the same happens with the healing length. So of course, here you have interactions that are too weak, but if you are going towards too much dense polariton fluid, then sound waves prevails and will destroy clustering dynamics in the system. So motivated by this proposal, we try to set up an experimental configuration that is able to capture these dynamics. So this is the experimental setup that we use. So we use one pulse laser to inject the fluid with a reference in order to get the interferogram and recover the phase. And at the same time, with another continuous wave laser modulated by an SLM, we arrive on the sample to create this ring barrier. So the pulse laser is shine at the center at different energy with respect to the bottom of the potential barrier. So in this case, we call it high energy because we are injecting the fluid with high kinetic energy, and this is called low energy because we are injecting the fluid with a much lower kinetic energy into the trap. Dissipation, the dissipation prevails due to the limited lifetime of polariton. This has been already cited many times in this conference. It is a similar experiment, let's say, in atomic BEC. So they have the possibility to recognize the sign of the vortices with the projection along one direction of the detection along one direction of the phase. They have some vortices at the end of the dynamics. They can classify in terms of dipoles, cluster, or free vortices, and depending on the initial condition, different temperature of the system can be recognized, where this part corresponds to the negative temperature regime with the formation of clustering in the system. So we can do something similar using exactly the same algorithm to detect our vortices. Here you see the position of vortices classified with the same color code in free vortices, clustering, and dipoles. And in the background, you see also the velocity streamlines. So here you have the evolution in time of the relative contribution of dipoles, clustered vortices, and free vortices, and you see that indeed, in the high energy case, there is the tendency of the system of accumulating vortices in cluster at the expenses of dipoles with respect to the low energy case. So this is very promising, and it already demonstrate that we can achieve this attractive interaction between same sign vortices. But actually, the true advantage of this system is the possibility to decompose the velocity field in the vortex contribution and wave contribution, and this allows us to separate the dynamics, and we can follow separately the evolution in time and space of the part of the kinetic energy that is incompressible component and the compressible component associated to vortices and waves. And this is important because then we can extract from that the incompressible kinetic energy spectrum of the system. And we see that with the low energy case doesn't show any plateau here that will correspond to this clustering, the onset of clustering dynamics, while in the high energy case, even if on a short range scale that corresponds more or less to the typical dimension inverse of the typical size of the cluster in the system, there is indeed a plateau. And this is a direct measurement. We can follow actually the evolution of this kinetic energy spectrum in time. So you see that after expansion, there is the injection of vortices more or less at the Healing length scale, and then there is this increasing in this part of the spectrum, and then after sometimes when the lifetime is already of this order of time, then we have decreasing of the excitation in the system. So this distance corresponds to the inverse of this one, and also the lifetime is, the time that it takes to form this kind of vortices is compatible with this short time scale of about 10, 20 picoseconds to form a small cluster of 3, 4, 5 vortices. So there is a question about this kind of dynamics. So in the case of atomic BEC, this evaporative heating mechanism has been proposed as the source of energy. So the average kinetic energy per vortex is increasing due to the losses of vortices out of the system. And while in our case, we don't have this kind of mechanism, the number of vortices is constant. What we have is many waves, sound waves in the system that are unavoidable for the way we use to inject vortices in the system. So we have decomposing the two contributions of kinetic energy. We can see that in the low energy case, the compressible part is always larger or equal to the incompressible one. While in the case where we see the onset of clustering, we see that the incompressible fraction of kinetic energy prevails. So we think that there is transpose of energy from the compressible part to the incompressible part, and this provides the fuel to increase the energy in the large-scale structure of the system. So I'm going to the second part of the talk. This is an image from the experiment. You see that we have these typical scales that corresponds to the vortex size, the intervortex distance, typical cluster size, and the trap size in the system. So we want to see what happens more or less in this region here. And for that, we analyze the statistic of the velocity difference. These are already compensated, but still we observe that there is no scaling. There are large exponential tails, and there is no rescaling of the curves. This is somehow expected because vortices in these quantum fluids are singular objects, and this kind of measurements between 2 points cannot avoid to see the presence of the singularity at the position of the vortex core. However, if we analyze instead the velocity circulation or the flux of vorticity into the system as a function of the radius of the area that we are considering, and then we compensate, we see that a perfect rescaling apart from area that are smaller than the Healing length. So this already shows that there is a similar scaling of velocity circulation in the system, and this suggests the idea that we can apply some kind of coarsening in the system, so we can apply the same measurement of velocity circulation, vorticity flux in the system, and when we arrive at the size of the vortex core, or a little bit more, the vortex distance, then we recognize even better than by vortex classification or correlation these areas, these regions of correlated vorticity in the system. This is not really dependent on the radius. There are a range of radius for which this works very well. So after a thresholding of this region, we can then apply some powerful tools that are provided by this machinery, the Schramm lower evolution curves. I will not enter into the details, but it is a real powerful and beautiful mathematical results with deep physical implication that allows to somehow connect our physical intuition of two-dimensional lattice model that explain ferromagnetism, percolation or structure of polymeric molecules and so on, with the universal scaling at the critical point for these universal models, and it provides some very powerful tools to predict the property of this kind of boundaries that we found at the critical point. So basically, these evolution curves map a Brownian motion. It's a family of curves that, depending on the mobility parameter, produce this kind of pattern, and this kind of pattern have universal scaling behaviors that are univocally associated to the lattice model. So in our case, this works quite well in the sense that we can measure, for example, the distribution of this region in terms of probability of finding a given area. And we see that as soon as we arrive at an area that corresponds to slightly larger the Healing length, we observe that the scaling emerge. So if we change the threshold, the scaling is the same, and the exponent is compatible with what is expected for two-dimensional percolation. This is nice. There are a number of predictions that we can check. Another one is the fractal dimension of these regions. And we see that, again, slightly above the Healing length, we found a nice scaling that is the same as predicted for the evolution curve with parameter 6 that correspond exactly to percolation. So now we have to be careful about that, because if we do the same, for example, on this kind of images, and we do some processing to obtain some kind of curves, we can obtain the same kind of scaling in some cases. This is, of course, due to the fact that this kind of universal behavior are not really telling us anything about the underlying process in the system. Anyway, there are some important conclusions that can be drawn out of that. So, first of all, this is, as I said, a powerful tool that allows to predict several statistical properties and correlation between these regions of correlated vorticity. And second, this is remarkably similar to what has been obtained already many years ago by Guido Boffetta in classical turbulence. So this shows that there are remarkable similarity between classical and quantum turbulence. Now, with that, I just want to resume the main results. So we are able to measure the onset of clustering either by classification of vortices and direct measurements of the kinetic energy spectrum. And we have also performed some analysis on the space distribution of this region, finding that they obey, they are conformal invariant, and they obey what is expected for models of percolation near the criticality. So in the future, I already mentioned to Riccardo the possibility of overcoming the limitation of the limited lifetime and to extend this kind of studies to quenches and thermalization. I also think that it will be very important to see the evolution of the work of Clement about the single-shot measurements, because these are still statistically relevant but averaging results. Then it's really important to probably look at half vortices. It's been mentioned in the talk by Salman and Marjana in this conference. Of course, interplay of sound wave and quantum vortices. And then really nice connection to the work of Thibault about the topological invariance in compressible quantum fluids. So a lot of connection. Thank you for your attention.
Thank you, Dario.
Okay, it works. So thank you very much. I have a question. When you imprint vortices optically, they are not hydrodynamic, right? In the sense that their healing length is not defined by interactions. It is defined by the profile that you imprinted. Do you need to wait some time so that they reshape due to interactions, or it doesn't matter for what you observe?
Yes, in principle, but this time is extremely fast with respect to the time it takes for this kind of dynamics to go on. So I expect in few picoseconds or less, they will adapt.
Thank you. Very nice talk. Can I also ask on timescales? I'm just a bit confused about the timescale sort of where you extract your measurements compared to the timescale of the vortex motion, for example. What's the comparative?
So we are observing this kind of dynamics over more than 100 picoseconds. That is corresponds more or less to the lifetime of this kind of sample. And in these measurements, we have the initial time that is just the expansion of the fluid. And then we have an interval of, let's say, 40 picoseconds in which this kind of clustering process takes place. After that, dissipation starts to prevail again, and we are...
Okay, I guess maybe I got confused because you showed a movie where you could actually see the motion of vortices. So it seemed there that you actually had resolution on the time scale of vortex motion.
Yes, we have resolution that is basically given by the pulse laser that we use as a reference in our holographic technique, that is about 2 picoseconds. So in principle, the resolution is, temporal resolution is of 2 picoseconds. However, it is not a proper tracking of the vortices because the technique works in a way where we take an image and then we take another image. Basically, these frames are relevant on a statistical sense, but we cannot really, or we are not sure, we cannot be sure that we can really follow the dynamics of single vortices. But in a statistical sense, then with that, you can actually do quench studies, yes, because statistic. Yes, absolutely.
I just wanted some clarification about the results you presented with the PDFs. If you could go back to that. I think it was the PDFs of the velocity and
this one.
Yeah, so here, I didn't quite understand. You said that, the earlier results when you looked at PDFs of the velocity, because you have this of the singular flow field around vortices, it causes an issue. So you go to work with the...
In this case.
Yeah. And so then you went to work with the vorticity, essentially.
Yes.
Which is actually, vorticity is just delta functions in this flow. It's also singular.
Well,
so are you using like a density-weighted velocity or what?
Yes, but in this case, you are considering the difference of velocity between 2 points. And if you get 1 point where there is a vortex, this is a singularity and it cannot be eliminated somehow. While when we consider the circulation of velocity, so in this case, vorticity can be singular at 1 point, but we take surface.
So it's an area integrated, yeah.
Yes, is the flux over this area. So changing the radius, as soon as we approach, let's say, the intervortex distance, or we can neutralize different vortices, and then this PDF collapse on a single line.
Thanks for the nice talk. Yeah, I've got also a question on the PDFs. From this, so for measuring the circulation at different areas, you would be in principle capable of seeing the scaling exponent of the moments of the circulation, because this has been, well, there are statistics in classical turbulence and in quantum turbulence. So is it too difficult? Does it because probably, I mean, you need a lot of scales, right?
Exactly. So it's in principle is possible. Limitations are on the range of scale that are available. So basically, then you have to. In this case, I think that this is not the best system or the best experiment to extract this kind of information, because, I mean, it's similar to other experiments that have been done, but it's not like really extended system where this maybe makes more sense.
Okay, and then another question also. I mean, the circulation, I mean, looks, I mean, a lot. I mean, it's self-similar. So the question, I mean, which arises is, but so if when you do the PDF of the velocity differences, if instead of the total velocity you took the incompressible velocity, would this change? So is it only depending on the vortices, on the singular, on the circular phase, or is there also a contribution from the compressibility?
So let me think, because we analyzed this point, just that now I'm not sure about the answer. However, I would say that it's still singular, also eliminating the contribution of vortices. Somehow it is still there. Now, I need to think and retake this data, but I don't think that this decomposition will help in obtaining this scale.
I also have a question. So I don't know, maybe I missed in the talk, but is there any difference fundamentally between turbulence in this driven dissipative setting as opposed to equilibrium condensates such as helium or atoms?
Well, actually, in those systems, you can reach really, especially in superfluid, you can really reach the full turbulent regime, the true turbulent regimes where you have these fluxes that are constant and this energy cascade. In this case, it is interesting because there is dissipation, and so this introduces a new constraint, a new time scale in the whole discussion, the time scale of dissipation. And so it becomes like a challenge to compensate, to accelerate the dynamics through intervortex distance and vortex-vortex interaction, basically due to density, to overcome this limitation. So there is an additional constraint in this case, but this does not prevent the onset of this kind of self-organization.
So if there are no more questions, let's thank Dario again.